Tonight, we are going to sit with one of the strangest possibilities modern physics has ever uncovered. A possibility so quiet, so difficult to picture clearly, that most people pass through their entire lives without ever realizing it exists. The possibility that time, the steady forward movement that seems to carry every moment of your life from future to present to past, may not actually be flowing at all. You experience time as motion. You feel it passing. You watch nights disappear into mornings, childhood disappear into memory, entire years slipping quietly away behind you. Time feels continuous and undeniable, as natural as gravity or breathing. And yet, when physicists look deeply into the equations that describe space, motion, relativity, and the structure of the universe itself, they encounter something unexpected. The equations do not always describe time as something moving forward. In some interpretations, they do not describe a flowing present at all. Over the next few hours, we will explore that idea slowly and without hurry. We will look at why human beings experience time the way we do, what Einstein's relativity revealed about the relationship between time and motion, why many physicists believe the distinction between past, present, and future may not be fundamental to reality itself, and what it could mean if every moment in time exists simultaneously, arranged not as a river that flows, but as a vast structure our minds experience only one piece at a time. There is nothing here that requires alarm. These questions have occupied physicists and philosophers for generations, and tonight we are simply allowing ourselves to sit beside them for a while, calmly and without urgency. Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. Let's begin. Chapter 1. What time feels like. There is a version of time that every person knows without being taught. It is the version you wake up inside each morning. Yesterday is behind you, fixed and unreachable. Tomorrow has not arrived. And the present moment, this one right now, is the only place where anything is actually happening. This is the time of memory and anticipation, of clocks and calendars, of the feeling that the world is continuously unfolding, second by second, in one direction only. This experienced time has a texture that is hard to describe but impossible to miss. It moves. It carries you forward. Some hours feel long and heavy, stretched out by waiting or discomfort, while others pass so quickly that you turn around, and an entire afternoon is gone. The pace of experienced time shifts depending on what you are doing, how old you are, and how closely you are paying attention. Children often describe summers that seem to last forever. Adults frequently find that years have collapsed into what felt like weeks. Experienced time is elastic, personal, and deeply tied to the quality of consciousness itself. Philosophers have written about this quality of time for thousands of years. The sense that the present moment is special, that it alone is real, while the past has vanished and the future does not yet exist, is one of the oldest and most persistent intuitions in human thought. The ancient Greeks distinguished between chronos, the measurable sequential time of hours and seasons, and kairos, the lived quality of a meaningful moment. Medieval thinkers debated whether time existed independently of the physical world, or only because conscious minds were present to perceive it. The question was never fully resolved. It was simply passed forward, generation by generation, to whoever was willing to sit with it next. What makes experienced time so convincing is precisely how consistent it is. Every person you have ever met shares the same basic relationship with it. No one experiences the future before the present. No one feels time running backward. The arrow of time, the direction from past to future, feels absolute, built into the fabric of existence rather than being a feature of how human minds happen to be organized. It feels less like a perception and more like a fact. And for most of human history, that was a reasonable way to think about it. Time was time. It passed. You measured it with sundials, then water clocks, then mechanical clocks, then atomic ones. Each instrument more precise than the last, each one confirming the same basic story. The seconds moved forward, the minutes accumulated, the hours were irreversible. Science and common experience agreed. But then, in the early years of the 20th century, a young physicist working quietly in a Swiss patent office began writing a set of papers that would, over the following decades, slowly and permanently unsettle that agreement. His name was Albert Einstein, and what he found, tucked inside the mathematics of light and motion, was that time was not at all the fixed, universal constant that everyone had assumed. It was something far more flexible, far more dependent on circumstance, and far more strange. That discovery did not immediately make the river of time disappear. People still aged, clocks still ticked, mornings still followed nights, but it opened a door, and once the door was open, physicists began to find things behind it that have never quite stopped being surprising. The story of what they found begins not with consciousness or philosophy, but with something much simpler: the speed of light and what happens when you take it seriously. Chapter 2: Einstein's Flexible Time. There is a question that seems almost too simple to take seriously. What would happen if you chased a beam of light? If light travels at a fixed speed and you move faster and faster in the same direction, would the light eventually appear to slow down relative to you, the way a car on the highway seems almost still when you pull up beside it at the same speed? Common sense says yes. Einstein said no. And the consequences of that single answer changed physics permanently. The principle Einstein began with was straightforward. The speed of light in a vacuum is constant. It does not matter how fast the source of the light is moving, and it does not matter how fast the observer is moving. Everyone in every situation measures light traveling at the same speed. That constancy is not an approximation. It is a fundamental feature of the universe, and once you accept it, something has to give. Because the everyday mathematics of speed, distance, and time no longer hold together the way they did before. What has to give, Einstein realized, is time itself. If two observers are moving at different speeds relative to each other, and both must measure light traveling at the same velocity, then their measurements of time cannot be identical. A clock moving through space at high speed will tick more slowly than a clock that is standing still. Not because of any mechanical flaw in the clock, not because of vibration or wear, but because time itself passes more slowly for the moving object. This effect is called time dilation, and it is not a theory in the casual sense of an educated guess. It has been measured directly many times with extraordinary precision. In 1971, physicists flew extremely accurate atomic clocks around the world on commercial aircraft and then compared them with identical clocks that had remained on the ground. The airborne clocks had fallen measurably behind, not by much, fractions of a microsecond, but the difference was real and matched Einstein's predictions almost exactly. The satellites that make up the global positioning system we rely on every day carry clocks that must be continuously corrected for time dilation, both from their speed and from the weaker gravity at their altitude. Without those corrections, navigation errors would accumulate rapidly and the entire system would become useless within hours. Time dilation is not a strange edge case that only appears in extreme laboratory conditions. It is a routine engineering consideration in the technology that guides aircraft, ships, and the devices in our pockets. Time moves at different rates depending on how fast you are moving and how strong the gravitational field around you is. That is not a metaphor. It is a measurable, operational reality. The deeper implication, though, is what matters most for our story. If time passes at different rates for different observers, then there is no single universal clock ticking away somewhere in the background, marking out an absolute present moment for the entire universe. Newton had imagined exactly that. A cosmic timekeeper running at a fixed rate regardless of where you were or how you were moving, providing a shared now for everything that existed. Einstein's equations removed that clock entirely. They replaced it with something far more local, far more personal, and far more dependent on the specific history of each observer's path through space. This is where the familiar feeling of time as a shared, universal flow begins to loosen. If your now and my now are not identical, if the rate at which time passes for each of us depends on factors like velocity and gravity, then the present moment is not a single line cutting cleanly across the universe. It is something more fragmented, more relative, more dependent on where you are and how you have been moving. Two observers in different locations moving at different speeds will disagree, in a precise and mathematically consistent way, about which events are happening simultaneously. There is no deeper fact that settles the disagreement in favor of one over the other. Both are correct within their own frame of reference. This relativity of simultaneity is one of the most disorienting results in all of physics. It means that the question of what is happening right now, elsewhere in the universe, does not have a single objective answer. Depending on your state of motion, the event you call simultaneous with this present moment could be something another observer would place firmly in the past or equally firmly in the future. The present, that thin and precious boundary between what has happened and what has not yet occurred, turns out to be observer dependent. For most practical purposes, on the surface of the Earth, moving at the speeds we normally encounter, these differences are so small as to be irrelevant. Your now and the now of someone sitting across the room from you are, for all daily purposes, the same. But the principle holds. And when physicists began to take it seriously, not just as a technical result, but as a statement about the nature of reality, it led them somewhere that is still being debated today, to the idea that past, present, and future may all exist simultaneously, and that time may not be a river at all, but something more like a landscape. Chapter 3. The Block Universe. If the present moment is not universal, if different observers moving at different speeds through space genuinely disagree about which events are happening simultaneously, with no deeper fact available to resolve the disagreement, then physics is pushed toward a conclusion that feels deeply strange when you first encounter it. The conclusion is this: the past, the present, and the future must all exist in the same sense, not sequentially, not one replacing the other, but together, simultaneously, as parts of a single four-dimensional structure. Physicists call this the block universe, and it follows not from speculation, but from the internal logic of relativity itself. The idea works like this. In ordinary three-dimensional space, we understand that places exist even when we are not looking at them. The city on the other side of the world is real right now, even though you cannot see it. Distance does not erase existence. The block universe extends that same reasoning into the dimension of time. Just as a distant place exists even though you are not there, a distant moment in time, a moment in the past, or a moment in the future, exists even though you are not experiencing it. In this picture, time is simply another dimension of a four-dimensional structure, and all of its contents are equally real, equally present in the fabric of what exists. The philosopher and physicist Hermann Minkowski, who had once been one of Einstein's mathematics teachers, was among the first to articulate this clearly. In 1908, he gave a lecture in which he described space and time as inseparable, merged into a single continuous structure he called space-time. His opening words at that lecture have stayed with physicists ever since. He declared that space by itself and time by itself were destined to fade into shadows, and that only a union of the two would preserve an independent reality. It was a striking claim, and the mathematics behind it was solid. Space and time were not two separate things. They were two aspects of one thing. In the block universe that emerges from this picture, every event that has ever occurred or will ever occur already has a fixed location in the four-dimensional fabric of space-time. The moment you were born occupies a specific coordinate in that structure. The moment you are in right now occupies another. The moments that lie ahead of you occupy others still. None of these coordinates disappears when it is no longer the present. They remain fixed in their positions, the way the coordinates of a mountain remain fixed whether you are standing on it or not. The present moment, in this picture, is not a special location in time. It is simply the location your consciousness currently occupies. This is a difficult idea to hold on to, because everything about our experience pushes against it. The past feels gone. The future feels genuinely absent, not merely hidden. The present feels like the only real thing there is. But the block universe does not say that your experience is wrong. It says that your experience is local. You are moving through space-time along a particular path. Physicists call it a world line. And the experience of time flowing is what it feels like from the inside to travel along that path. The flow is real as an experience. What may not be real is the idea that the flow corresponds to something happening in the external structure of the universe. The river is not in the landscape, it is in the traveler. One way to approach this is to think about how a novel works. Every page of a novel exists simultaneously in the physical book. The ending is there, printed and waiting, even as a reader sits with the opening chapter. The characters within the story, if they could be said to experience anything, would feel their story unfolding moment by moment. They would have no sense of the later chapters already existing. Their experience of narrative time would feel real and forward-moving. But from outside the book, a different perspective is available. One where all of the moments coexist, none more real than any other. The block universe suggests that the universe may be something like that book, and that we are something like those characters, experiencing a sequential journey through a structure that, from a broader perspective, simply is. Physicists who work with general relativity often find the block universe to be the most natural reading of the mathematics. The equations do not contain a moving present. They do not distinguish between past and future in any fundamental way. They describe a static four-dimensional geometry and everything that we associate with the passage of time. The sequence of events, the sense of now, the difference between memory and anticipation, must be explained in some other way, as features of observers within the block, rather than features of the block itself. That explanation is not simple, and it is not complete. The block universe raises as many questions as it answers. If all moments exist equally, why do we experience only one at a time? Why does experience move in one direction rather than the other? Why does the past feel different from the future? if the equations treat them symmetrically? These are the questions that the next chapters will sit with, carefully and without hurry. Chapter 4. Why time has a direction. If the block universe is correct, and the equations of physics treat past and future symmetrically, then one of the most basic features of our experience becomes genuinely puzzling. You remember yesterday, but not tomorrow. You can stir cream into coffee, but you cannot unstir it. You can shatter a glass, but you have never watched a shattered glass reassemble itself from the floor. Time, as we live it, has a very clear direction. Things move from order toward disorder, from the intact toward the broken, from the concentrated toward the dispersed. And yet the fundamental equations of physics, the ones describing how particles move and interact at the deepest level, work equally well in both directions. Run them forward and they describe the world correctly. Run them backward and they remain mathematically valid. The equations themselves do not know which way time is supposed to go. This asymmetry between the time-symmetric equations of physics and the clearly directional time of everyday experience is one of the deepest unsolved problems in all of science. The technical name for it involves a concept called entropy, and the law that governs it is the second law of thermodynamics. That law states, in its simplest form, that the total entropy of a closed system tends to increase over time. Entropy is a measure of disorder, of the number of ways the components of a system can be arranged. A tidy room has low entropy. The same room, after a week of neglect, has higher entropy. There are vastly more ways for things to be disordered than for them to be ordered, and so systems naturally drift toward disorder simply because disordered states are overwhelmingly more probable. The Austrian physicist Ludwig Boltzmann worked out the statistical foundations of this idea in the latter half of the 19th century, and his work remains one of the great achievements of theoretical physics. What Boltzmann showed was that the second law is not absolute in the way that, say, conservation of energy is absolute. It is statistical. On the scale of atoms and molecules, time-reverse processes are technically possible. A broken glass could theoretically reassemble. Cream could theoretically separate itself back out of coffee. These events are not forbidden by the laws of physics. They are simply so astronomically improbable that they never happen in practice. The arrow of time, in Boltzmann's picture, is not written into the fundamental equations. It is a consequence of probability on a vast scale. But this explanation, elegant as it is, immediately raises a deeper question. If entropy increases because high entropy states are more probable than low entropy states, then why was the entropy of the universe so extraordinarily low to begin with? The arrow of time points from low entropy to high entropy. For that arrow to exist, there must have been a starting point of very low entropy, and the universe, as best as physicists can determine, began in an exceptionally ordered, exceptionally low entropy state at the moment of the Big Bang. The expansion that followed has been, in a sense, a slow and majestic unwinding of that initial order, a process that has been generating stars, galaxies, planets, life, and the experience of time's passage ever since. The cosmologist Roger Penrose has spent decades thinking carefully about this problem, and his calculations suggest that the initial low entropy state of the universe was extraordinarily precise, fine-tuned to a degree that is almost impossible to communicate in ordinary language. The ordered beginning is not something the laws of physics required. It is something that happened, and its happening is what gave time its direction. Without that unusually ordered starting point, there would be no arrow. Without the arrow, there would be no difference between past and future. Without that difference, The experience of time flowing in one direction, of memory pointing backward and anticipation pointing forward, would not exist in any recognizable form. This is a strange kind of explanation. The direction of time, one of the most immediate and certain features of our experience, turns out to rest not on a fundamental law, but on a cosmological accident, on the particular initial conditions of a universe that did not have to begin the way it did. The asymmetry we feel so viscerally every time something breaks, every time we grow older, every time a memory forms, is ultimately rooted in the state of the universe 14 billion years ago. There is something quietly humbling about that, the feeling of time moving forward, the very thing that makes a life feel like a story, with a beginning that recedes and an ending that approaches, is a consequence of where we find ourselves in the long, slow increase of cosmic entropy. We are not at the beginning of that process, and we are not near the end. We are somewhere in the middle of an unimaginably vast unwinding, and our experience of time as directional and irreversible is simply what it feels like to exist at this particular location in that process. The equations of physics, run forward or backward, remain indifferent. The universe, beginning from conditions of remarkable order, gave time its arrow, and we, moving along our world lines through the block universe, experience that arrow as the most natural and obvious thing in the world. Chapter 5. The Present Moment. There is a word that carries more weight than almost any other in the human experience of time. That word is now. It seems self-evident, immediate, and beyond question. Whatever else might be uncertain about the nature of time, the present moment feels like solid ground. You are here in this moment, and that is the most certain thing there is. And yet, when physicists and philosophers examine the present moment carefully, they find that it is one of the hardest things in all of physics to locate, define, or defend. The difficulty begins with something simple. The information that reaches your senses does not arrive instantaneously. Light takes time to travel from the objects around you to your eyes. Sound takes time to travel from its source to your ears. The signals that carry sensory information along your nerves take time to reach your brain, and your brain takes additional time to process and assemble them into a coherent experience. The moment you perceive as now is not the moment the events around you are occurring. It is a slightly delayed reconstruction, assembled from signals that left their sources a small but measurable time before you became aware of them. For ordinary life, these delays are so small that they make no practical difference. The gap between the event and your experience of it is measured in milliseconds, and your brain compensates for it so smoothly that you never notice. But the principle matters. Your experience of the present is already, in a precise physical sense, an experience of the very recent past. The now you inhabit is always slightly behind the now of the physical world around you. Extend that gap further, and the problem deepens considerably. When you look at the moon, you are seeing it as it was roughly 1¼ seconds ago. When you look at the sun, you are seeing it as it was about 8 minutes ago. When you look at the nearest star beyond our own sun, you are looking at light that left its source more than 4 years before it reached your eye. When you look at a distant galaxy, the light arriving at your eye may have been traveling for millions or billions of years. The universe you observe at any moment is not the universe as it currently is. It is a vast collection of images from different moments in the past, layered together into something that looks, from our position, like a single simultaneous view. There is no observation point from which the entire universe can be seen as it is right now. Every observation is an observation of the past, at a distance determined by how long it took the light to arrive. The present moment, as a universal condition shared by everything in existence, is not something that can be observed or verified. It can only be inferred, and as relativity makes clear, different observers will infer different things. Physicists sometimes describe this by saying that there is no preferred foliation of space-time. A foliation, in this context, means a way of slicing the four-dimensional block into a series of three-dimensional snapshots, each one representing a moment in time. In everyday life, we assume that such slices are natural and obvious, that the universe can be cleanly divided into a series of nows, each one following the previous. But relativity shows that there is no unique, physically preferred way to make those cuts. Different observers, moving differently through space, will carve up space-time into different sequences of moments. Each carving is internally consistent. None of them is the correct one. This does not mean that the present moment is meaningless. For any individual observer, the local present is perfectly well defined. You know what is happening around you right now, within the limits of how quickly information can reach you. What relativity removes is the global present, the idea that there exists, at this moment, a single simultaneous slice of reality that encompasses everything in the universe at once. That idea, which feels so natural and so obvious, turns out to have no firm foundation in the physics of space-time. Some physicists find this conclusion liberating. It suggests that reality is not a single unfolding story with one present moment advancing through it, but something richer and more complex. A four-dimensional structure in which every observer carries their own local experience of now, and in which no single now has special status. Others find it deeply uncomfortable because it seems to erase something that feels absolutely fundamental to what it means to exist. The tension between those two reactions has driven some of the most productive and unresolved debates in the philosophy of physics. What both sides agree on is this: the present moment, as physics currently understands it, is not the simple, universal, self-evident thing it appears to be from the inside. It is local, observer-dependent, and constructed, assembled by minds moving through a space-time that does not, at its deepest level, distinguish between now and then in any absolute way. The ground that felt most solid turns out, on close inspection, to be the most subtle ground of all. Chapter 6. Quantum Time. There is a point in the study of physics where the strangeness of time, already considerable after relativity, deepens further still. That point is the boundary where relativity ends and quantum mechanics begins. These two theories are the twin foundations of modern physics. Between them, they describe almost everything that has been measured, tested, and confirmed about the physical world. Relativity governs the very large, the structure of space-time, the behavior of gravity, the geometry of the cosmos. Quantum mechanics governs the very small, the behavior of particles, the nature of energy, the probabilistic foundations of matter. Each theory is extraordinarily successful within its own domain, and yet they do not fit together cleanly. And one of the places where the friction between them is most visible is in their treatment of time. In relativity, time is a dimension. It is woven into the fabric of space-time on equal footing with the three dimensions of space, and it behaves dynamically, stretching and compressing in response to gravity and motion. Time in relativity is something the universe does, something that participates in the geometry of reality rather than simply providing a backdrop against which events occur. In quantum mechanics, time is treated very differently. It appears in the equations not as a dynamic participant, but as an external parameter, a fixed backdrop against which quantum events unfold. The famous equation written by Erwin Schrödinger in 1926, which describes how quantum systems evolve, treats time as something given from outside the system rather than something the system itself generates or shapes. This is a profound difference, and it becomes a serious problem when physicists attempt to combine the two theories into a single unified description of nature. The most direct attempt to do this produced an equation developed in the 1960s by the physicists John Wheeler and Bryce DeWitt. Their equation, now known simply as the Wheeler-DeWitt equation, was intended to describe the quantum state of the entire universe. It was a significant and ambitious undertaking, and the equation itself is mathematically striking. But it contains something deeply puzzling. Time does not appear in it. The Wheeler-DeWitt equation describes the universe as a static object, a quantum state with no time variable, no evolution, no before or after. The universe in this equation simply is. It does not change. It does not move through time. It exists as a single, timeless structure. This result has troubled physicists ever since the equation was first written down, and it has generated a range of responses. Some physicists treat the absence of time as a technical problem to be solved, a sign that the equation is incomplete, or that it has been set up in a way that inadvertently removes time from the picture. Others take it more seriously, as a genuine hint that time, at the most fundamental level of physical description, may not be a basic ingredient of reality at all. On this view, time is something that emerges, something that appears when you look at the universe from within, as a local observer with limited access to the whole, rather than something that exists as a fundamental feature of the underlying structure. The physicist Carlo Rovelli has explored this idea with particular depth and care. In his work on quantum gravity, Rovelli argues that the absence of time in the fundamental equations is not a problem to be fixed, but a feature to be understood. He suggests that time as we experience it, flowing, directional, divided into past and future, is not written into the bedrock of physics. It emerges from the way complex systems with many degrees of freedom interact with their environments. A simple system of a handful of particles, described completely and exactly, would have no time. A complex system, like a human brain, embedded in a world of countless interacting parts, generates the experience of time as a kind of thermodynamic shadow, a consequence of entropy, incomplete information, and the particular perspective of an observer who cannot see the whole. This is a striking inversion of the ordinary picture. We tend to think of time as the most basic framework within which everything else happens. Rovelli's view suggests instead that time is one of the last things to appear, a high-level feature that emerges from complexity and perspective, the way that temperature emerges from the collective motion of molecules rather than being a property of any individual one. No single molecule is hot or cold. Temperature is what you measure when you have enough molecules interacting that their average behavior becomes meaningful. In a similar way, no single quantum event happens in time. Time is what you experience when you are a complex observer embedded in a universe of vast and irreducible entanglement. Quantum mechanics also introduces another layer of strangeness that bears on the nature of time. In the quantum world, events do not have definite outcomes until they are measured or observed. A particle does not have a precise position or momentum until an interaction forces one of those properties into definiteness. This indeterminacy is not a reflection of ignorance. It is not that the particle has a definite position, and we simply do not know it. The indeterminacy is real, built into the structure of quantum reality, and it raises a quiet but persistent question about the relationship between time and observation. If events do not fully exist until they are observed, and if observation is always something that happens in the local present of some particular observer, then the present moment acquires a strange kind of creative role. Not just the location where reality is experienced, but potentially the location where certain aspects of reality are brought into being. Physicists disagree sharply about how seriously to take this implication. Some interpretations of quantum mechanics, such as the many worlds interpretation developed by Hugh Everett in 1957, avoid it entirely by saying that all possible outcomes of every quantum event occur simultaneously in branching versions of reality, with no special role for observation or the present moment. Others, including various forms of the Copenhagen interpretation that dominated physics for much of the 20th century, place the act of measurement at the center of the story and leave the question of what is happening between measurements deliberately unanswered. The debate between these interpretations has not been resolved, and it may not be resolvable by experiment alone, because the interpretations often make identical predictions while describing reality in fundamentally different ways. What all of this leaves us with is a picture of time that is far more layered and uncertain than the one we begin with as children. At the scale of everyday life, time flows steadily and in one direction, and nothing about that experience is wrong or illusory. At the scale of relativity, time stretches and compresses, simultaneity dissolves, and the present moment loses its universal status. At the scale of quantum gravity, time may disappear from the equations entirely, emerging only as a feature of complex systems viewed from within. The deeper you look, the less time resembles the simple, steady river it appears to be from the surface. Chapter 7. The Experience of Flow. There is a question that sits at the center of everything we have explored so far, and it is not a question about equations or cosmology. It is a question about you. If time does not flow at the fundamental level of physics, if the block universe is static, if the present moment has no universal status, if time disappears entirely from the deepest equations, then why does it feel so completely and overwhelmingly as though it does? Why is the experience of time passing not just present, but insistent, continuous, and impossible to set aside even for a moment? This is not a question physics alone can answer. It sits at the intersection of neuroscience, psychology, philosophy of mind, and physics, and each of those fields approaches it from a different angle. But together, they sketch a picture that is, in its own way, as strange as anything relativity or quantum mechanics has offered. The experience of time flowing is real. It is one of the most reliable features of conscious life, and it may be something the brain constructs, actively, continuously, and with considerable effort, rather than something it simply receives from the world. The neuroscience of time perception is a young and rapidly developing field, and its findings are already surprising. The brain does not have a single dedicated organ for measuring time, the way the eye is dedicated to light or the ear to sound. Instead, the perception of time is distributed across multiple systems, assembled from different streams of information, and heavily influenced by attention, emotion, memory, and expectation. The same interval of clock time can feel very different depending on the circumstances. A minute spent waiting for news that matters feels nothing like a minute spent absorbed in something you love. A frightening experience can seem to slow time almost to a standstill, while a pleasant one can make hours vanish without trace. Neuroscientists have identified several distinct aspects of time perception that the brain handles separately. There is the perception of very short intervals measured in milliseconds, which is handled largely by the cerebellum and is closely tied to motor control and the coordination of movement. There is the perception of durations in the range of seconds to minutes, which involves the basal ganglia and prefrontal cortex and is strongly affected by dopamine levels and emotional state. And there is the broader sense of time at the scale of days, weeks, and years. Autobiographical time, the time of memory and personal history, which involves the hippocampus and the systems that encode and retrieve episodes from the past. These systems do not always agree with each other, and they do not always agree with the clock. What they collectively produce is not a direct readout of objective time, but a constructed narrative, a story the brain tells about when things happened, how long they lasted, and in what order they occurred. That narrative is usually accurate enough for practical purposes, but it is a narrative assembled from imperfect information, shaped by the priorities and limitations of a biological system that evolved to survive rather than to measure time with precision. One of the most striking findings in this area concerns the way the brain handles the present moment itself. Experiments in timing and perception have shown that what we experience as now is not a point, but a window, a brief interval of time, roughly 2 to 3 seconds in duration, within which events are bound together into a single experienced moment. Stimuli that fall within this window are perceived as simultaneous or as part of the same experience, even if they are not strictly coincident. The brain stitches them together, smoothing over the small gaps and delays, presenting consciousness with a unified now that is already an editorial product rather than a raw feed from the world. This window has been called the specious present by psychologists, a term introduced in the 19th century to capture the idea that the present moment, as experienced, has a small but definite duration, rather than being an infinitely thin instant. Within that window, time is experienced as a kind of thick now, rich with immediately preceding context and immediate anticipation of what is about to happen. The sense of flow, of one moment moving into the next, may be partly a product of how these windows overlap and connect, each one carrying forward a trace of the previous and an expectation of the next, creating the sensation of continuous movement through time. Memory plays a central role in this construction. The feeling that time has passed, the retrospective sense of duration, is closely tied to how many distinct memories were formed during an interval. When a period of time is filled with new experiences, novel environments, and events worth encoding, it tends to feel long in retrospect. When a period is routine and repetitive, offering little that is new enough to store, it tends to feel short in retrospect, even if it felt long in the moment. This is why childhood, filled with firsts and novelties, often feels vast in memory, while decades of adult routine can compress into what feels like a short time when looked back upon. The philosopher Henry Bergson, writing in the late 19th and early 20th centuries, argued that the lived experience of time, what he called duration, was fundamentally different from the mathematical time of physics, and that science, in measuring and dividing time into units, was capturing something real, but missing something essential. The flow of time as experienced, Bergson thought, was not reducible to a sequence of instants. It was more like music, something whose meaning existed precisely in its movement, and which could not be understood by freezing any single moment and examining it in isolation. His ideas fell out of fashion as physics advanced, but neuroscience has returned to some of his intuitions from a different direction, finding that the brain does indeed process time in ways that resist reduction to simple measurement. What all of this suggests is that the flow of time is not something beamed directly into consciousness from the structure of the universe. It is something the brain builds using memory, anticipation, attention, and the continuous threading of moments into narrative. The river we experience is not out there in the landscape of space-time. It is assembled moment by moment inside the mind of the observer, which may be why it feels so immediate and so real, and why it persists so stubbornly, even when physics suggests that the landscape it seems to flow through may be, at its deepest level, perfectly still. Chapter 8. Arrows and Illusions. There is a word that appears frequently in discussions of time and physics, and it is a word worth approaching carefully. That word is illusion. When physicists or philosophers suggest that the flow of time might be an illusion, they are sometimes taken to mean that time is not real, that our experience of it is a mistake, that the hours and years of a human life are somehow less genuine than the equations that describe them. That is not what is meant. The claim is more subtle, and in some ways more interesting, than a simple dismissal of experience. An illusion, in the philosophical sense relevant here, is not a hallucination or an error. It is a case where the appearance of something differs systematically from its underlying nature. The way the sun appears to move across the sky is an illusion in this sense. The sun is not moving relative to the earth in the way it appears to move, but the appearance itself is perfectly real, generated by a genuine physical process, namely the rotation of the earth. No one who understands the astronomy thinks the sunrise is unreal. They simply understand that what they are seeing is a particular perspective on something whose underlying structure is different from what the view suggests. The suggestion that the flow of time might be an illusion in this sense means something similar. The experience of flow is real. The sequence of moments, the sense of one thing following another, the feeling of being carried forward through life. None of that is being dismissed. What is being questioned is whether that experience corresponds to something happening in the external structure of the universe, or whether it is a feature of how minds like ours process and represent a reality that is, at its foundation, structured very differently from how it appears. Consider what it would mean for the flow to be real in the fullest sense, for time to genuinely pass at the level of fundamental physics, for the present moment to be a real and universal feature of the universe, for the future to genuinely not yet exist, and the past to genuinely be gone. For this to be the case, physics would need to contain some mechanism that picks out a present moment, advances it forward, and distinguishes the existing present from the non-existing past and future. No such mechanism has been found. The equations of physics, as currently understood, do not contain anything that plays this role. The passing of time, in the sense of a present moment that moves through the block universe like a spotlight advancing through a darkened theatre, is nowhere to be found in the fundamental description of nature. This absence is not a gap waiting to be filled by a future discovery. It may be a genuine feature of the way reality is structured. The physicist Lee Smolin, one of the few prominent voices in contemporary physics who argues strongly for the reality of time's passage, has spent years trying to construct a framework in which time is fundamental rather than emergent. His work is a serious and carefully reasoned attempt to push back against the block universe picture, and it has generated productive debate. But even Smolin acknowledges that the standard formulation of both relativity and quantum mechanics does not naturally accommodate a moving present. His project is, in part, a project of rebuilding physics from the ground up in a way that restores time to a fundamental role. And that project remains incomplete and contested. For most physicists working within the standard framework, the more natural conclusion is that the passage of time is something that emerges, something that appears at the level of complex, entropy-generating, memory-forming systems embedded in the block universe, rather than something present at the level of the fundamental equations. On this view, the arrow of time, the sense of flow, and the privileged status of the present moment are all features of a particular kind of observer interacting with a particular kind of environment, rather than features of space-time itself. This perspective has a long and respectable history in physics. Many of the properties we regard as most basic and most real turn out, on close examination, to be emergent rather than fundamental. Temperature, as noted earlier, is not a property of individual molecules. It is a collective property that appears when many molecules interact. Color is not a property of light itself, but a feature of how certain visual systems respond to different wavelengths. Solidity, the hardness of a table, the firmness of the ground, is not a fundamental property of matter, but a consequence of electromagnetic forces between atoms that prevent them from passing through each other. The world is full of properties that feel primary and irreducible, but turn out to rest on something quite different underneath. Time may be another such property. The flow, the direction, the privileged present. These may be the way a certain kind of mind, operating within a certain kind of thermodynamic environment, experiences a four-dimensional structure that does not, at its own level, flow or advance or distinguish between now and then. That experience is not wrong. It is not a failure of perception. It is simply the view from inside, the only view available to beings like us, and a view that is entirely appropriate for navigating the world we inhabit. There is something worth sitting with in that idea. The flow of time, which feels like the most given and most unchosen feature of existence, may be one of the most remarkable things a mind does. Not a passive reception of something happening in the universe, but an active construction, a way of being in a world that does not, at its deepest level, move at all. The river is not in the landscape. It is in the way we move through it, and perhaps in the movement itself. Chapter 9. Living in a Timeless Universe. There is a point in any long exploration of ideas where the abstract begins to feel personal. We have moved through relativity and block universes, through entropy and quantum equations, through the neuroscience of perception and the philosophy of illusion. And somewhere in that journey, a question begins to form that is quieter and more intimate than any of the technical ones. If time does not flow at the fundamental level of reality, if the past and future are as real as the present, if every moment of a human life exists permanently in the fabric of space-time, what does that mean for the way we actually live? What does it mean for memory, for loss, for the people and places that time seems to carry away from us? These are not questions physics can answer directly. Physics can describe the structure of space-time. It can tell us about the geometry of the block universe and the statistical origins of the arrow of time. But it does not tell us how to feel about any of it, and it does not resolve the deep human need to make sense of a life that is experienced as moving through time, even if, at some deeper level, it simply exists within it. Philosophy and human experience have to carry the weight here, and they have been doing so for a very long time. One of the most striking implications of the block universe is what it suggests about the past. In ordinary experience, the past is gone. The people you have lost are absent. The moments you treasured are over. Time carries everything away, and the carrying away is one of the most painful features of existence. Grief is in large part a response to this, to the irreversibility of loss, to the fact that what was present is now permanently absent. The block universe does not eliminate grief, and it does not make loss easy, but it does offer a different way of thinking about what the past is. If every moment in time exists as a permanent coordinate in the four-dimensional structure of space-time, then the moments that have passed have not been destroyed. They are still there, fixed in their positions in the block, as real as the present moment, as real as any moment that has not yet arrived. The conversation you had years ago with someone you loved, the afternoon light of a particular summer, the sound of a voice you will never hear again in the ordinary sense. These are not gone in the way that a fire goes out or a wave collapses back into the sea. They exist in the block universe as permanent features of space-time. They are simply not here, not at your current coordinate. They are there at theirs. This is not a comfortable idea in any simple way, and it would be dishonest to present it as a cure for grief or a reason not to feel the weight of loss. The inaccessibility of the past is real. You cannot return to those coordinates. Your world line moves in one direction only, tracing a path through the block that does not double back. But there is something in the permanence of the past, in the idea that it continues to exist rather than having been erased, that some people find quietly meaningful. The physicist Brian Greene has written about this in the context of his own experience of loss, noting that the block universe picture offers a kind of comfort that is different from the comfort of religion or memory, rooted not in hope or imagination, but in the actual structure of space-time as physics currently understands it. The future presents a different kind of challenge. If the block universe is correct, and the future exists just as fully as the present and the past, then every moment of your life that has not yet arrived is already there, already fixed, already part of the permanent structure of space-time. This raises the question of free will in a form that is difficult to sidestep. If the future already exists, in what sense are your choices genuinely open? In what sense do you decide anything, if what you will decide is already, in some sense, determined by a coordinate in the block that simply has not been reached yet? This is one of the oldest problems in philosophy, and the block universe gives it a new and sharper form. Physicists and philosophers who take the block universe seriously have responded to it in various ways. Some argue that the block universe is fully compatible with free will, because free will is not about the future being undetermined in some cosmic sense, but about the process by which decisions are made. Your choices are the result of your reasoning, your values, your character. And the fact that those choices are, in the block universe picture, already fixed, does not mean they are not genuinely yours. The fixedness is not a constraint imposed from outside. It is simply a description of what you, being who you are, will in fact do. Others find this response unsatisfying and argue that a genuine block universe, in which the future is as real and as settled as the past, leaves no meaningful room for agency. The debate is unresolved, and it may remain so, because it touches on questions about consciousness and causation that physics alone cannot settle. What it does suggest, at minimum, is that the relationship between the structure of time and the experience of making choices is far more complicated than it appears from the inside. There is another dimension to living in a timeless universe that is worth considering slowly. If time does not flow, if the present moment has no special cosmic status, if the universe is a four-dimensional block rather than an unfolding story, then in a certain sense, nothing is ever truly lost, and nothing is ever truly finished. Every moment of joy, every moment of difficulty, every ordinary Tuesday afternoon, every night of deep sleep and slow dreaming, all of it exists permanently and completely at its coordinate in the block. The universe does not consume its moments and discard them. It contains them, all of them, always. That is a strange kind of permanence. It does not feel like the permanence we usually hope for, because it is not accessible. You cannot visit the past coordinates. You cannot slow your progress through the block or choose a different direction. You are moving always along the world line that your particular configuration of matter and memory and intention traces through the four-dimensional structure of space-time. But the moving does not erase what has been. It simply leaves it behind, the way a traveler leaves a city behind, without the city ceasing to exist. There is a quiet kind of steadiness available in that thought, if you are willing to sit with it long enough. Not a resolution, not an answer to the hardest questions about time and loss and choice. Simply a different way of holding the fact of existence, one that places every moment, including this one, in a permanent relation to every other, in a universe that does not move but contains, in its still and vast geometry, everything that has ever been and everything that is yet to come. Chapter 10. Time and Consciousness. There is a connection that runs through everything we have explored so far, present in nearly every chapter without ever being made fully explicit. That connection is consciousness. The block universe is static, but it is conscious observers who experience it as moving. The arrow of time emerges from entropy, but it is conscious minds that encode that arrow as memory. The present moment has no universal physical status, but it is the center of every conscious experience that has ever occurred. Wherever the investigation of time leads, it keeps arriving at the same threshold, the boundary between the physical description of the universe and the inner life of the beings who inhabit it. This is not a coincidence. It reflects something deep about the nature of the problem. Time, as a philosophical and scientific puzzle, is unusual in that it exists simultaneously as an objective feature of the physical world and as the most immediate and inescapable dimension of subjective experience. Almost every other topic in physics can be discussed entirely from the outside, as a feature of the world that exists independently of any observer. Time cannot. The moment you ask what time really is, you find yourself asking about the relationship between the external structure of space-time and the internal structure of experience. And that relationship is one of the most difficult and least understood things in all of science. The philosopher David Chalmers has called the problem of consciousness the hard problem, not because the science of the brain is unimportant or uninteresting, but because explaining the physical mechanisms of perception and cognition, however completely, seems to leave something out. It leaves out the question of why there is something it is like to be a conscious creature at all. Why does the processing of information in a brain give rise to an inner experience, to the felt quality of seeing red, hearing music, or sensing the passage of time, rather than simply occurring in the dark without any accompanying awareness? That question has not been answered, and some philosophers believe it may never be fully answered within the framework of physical science as currently conceived. The experience of time is one of the places where the hard problem cuts deepest. We can describe in considerable detail what the brain does when it processes temporal information. We can identify the neural systems involved in short interval timing, in the perception of duration, in the construction of the specious present. We can explain, at least in outline, why the brain generates a sense of flow and direction, but explaining the mechanism does not explain why that mechanism is accompanied by the vivid, immediate, first-person experience of time passing, why it feels like anything at all to be a creature moving through time, rather than simply being a physical system processing temporal information without any inner dimension. Some thinkers have suggested that this gap between mechanism and experience points towards something important about the nature of consciousness itself. That consciousness may not be simply a product of physical processes, but may be in some sense fundamental to reality, present not just in biological brains, but woven into the fabric of existence at a deeper level. This view, known in various forms as panpsychism, has a long philosophical history and has recently attracted renewed attention from a number of serious philosophers and scientists. If consciousness is fundamental, then the relationship between time and experience takes on a different character. Time would not be something that exists independently of mind and is then perceived by it. It would be something that arises in and through the relationship between consciousness and the physical world, inseparable from the act of experiencing itself. This is a speculative direction, and it should be held lightly, but it points towards something worth considering. Our entire investigation of time has proceeded by moving from the familiar surface of experience down toward the unfamiliar depths of physics, and at every level we have found that time becomes less solid, less obvious, and more dependent on the perspective of the observer. Relativity showed us that time is local. Thermodynamics showed us that its direction is statistical. Quantum gravity suggested that it may not be fundamental at all. And now, at the level of consciousness, we find that the very experience of time, the flow, the now, the irreversible movement from past to future, may be something that minds generate rather than something they simply receive. If that is correct, then consciousness is not a passive witness to the passage of time. It is, in some sense, the place where time happens, not in a way that contradicts the physics. The block universe does not require a mind to exist, and the geometry of space-time is not produced by human experience. But the flowing, the moving, the sense of one moment giving way to the next, these may be features of a certain kind of inner life, rather than features of the outer world. The universe, in this picture, contains time as a dimension. Minds experience time as a river, and the river exists not in the landscape, but in the travelling. There is a long tradition in both Eastern and Western philosophy of treating the present moment as something special, not because physics privileges it, but because it is the only place where experience actually occurs. The past exists as memory, which is a present mental state. The future exists as anticipation, which is also a present mental state. All of experience, regardless of its content, happens now, in the immediate living present of a conscious mind. Meditation traditions have built entire practices around the cultivation of presence, around the effort to inhabit the present moment more fully and with less distraction from the pull of memory and anticipation. These practices do not require any particular view about the physics of time. They simply take seriously the fact that experience is always and only present, whatever the underlying structure of the universe may be. Physics tells us the present has no universal status. Contemplative traditions tell us the present is the only place we ever actually are. These two claims are not as contradictory as they might first appear. Physics is describing the structure of the external world. Contemplative traditions are describing the structure of inner experience. Both can be true at once. The present moment may be physically unremarkable and experientially irreplaceable, a local, constructed, observer-dependent feature of a timeless universe, and simultaneously the only ground on which a conscious life is ever actually lived. What the science of time ultimately offers is not a replacement for experience, but a deepening of it. Knowing that the flow of time is constructed rather than given does not make the flow less real as an experience. It makes it more remarkable. The brain's ability to assemble a coherent, continuous, directional experience of time from the raw material of a static four-dimensional geometry is not a limitation or a mistake. It is one of the most extraordinary things that matter has ever done. A feat of organization and integration so seamless that it took centuries of physics and philosophy to begin to see the seams. Chapter 11. What remains? There is a particular kind of question that good science tends to leave behind. Not the questions it answers, but the ones it opens. The ones that were not visible before the investigation began, that only become visible once enough of the landscape has been cleared. The investigation into the nature of time is full of such questions. We began with something that seemed obvious and arrived somewhere that feels genuinely open, and that openness is not a failure. It is what honest inquiry looks like when it is working. Physics has told us several things about time that are now very difficult to set aside. It has told us that time is not universal, that it passes at different rates depending on speed and gravity, that two clocks separated by motion or altitude will disagree about how much time has elapsed between the same two events. It has told us that simultaneity is relative, that the question of what is happening right now, elsewhere in the universe, does not have a single objective answer, but depends on the state of motion of the observer asking it. It has told us that the fundamental equations of physics, when applied to the universe as a whole, do not contain a time variable at all, that the deepest mathematical description of nature we currently possess is, in a precise technical sense, timeless. And yet, here we are, inside time, moving through it, shaped by it in every possible way. The tension between those two facts, the timelessness of the equations and the overwhelming temporality of experience, is not something that has been resolved. It sits at the center of some of the most active and unresolved debates in contemporary physics and philosophy of mind. Physicists like Carlo Rovelli argue that time emerges from complexity and entanglement, that it is a feature of observers rather than of the observed. Physicists like Lee Smolin argue the opposite, that time is the most fundamental thing there is, and that the apparent timelessness of our equations reflects a limitation in how we have chosen to write them, rather than a genuine feature of reality. Both positions are held by serious, careful thinkers, and neither has yet produced a result decisive enough to settle the argument. What we are left with is a situation that requires a particular kind of intellectual comfort, the comfort of not knowing, of holding a question open without forcing it toward a resolution it has not yet earned. This is not a comfortable posture for minds that are built to seek answers and close loops, but it is the honest posture, and there is a kind of rest available in it, once you stop fighting the uncertainty and allow it to simply be there. The philosopher Ludwig Wittgenstein once observed that the deepest problems are not solved, but dissolved, that they lose their grip not because we find the answer, but because we come to understand the question differently. The problem of time may be like that. The question of whether time really flows may not be a question that admits of a clean empirical answer, because the flowing is something that happens in experience, and experience is not fully captured by the equations that describe the physical world. The equations and the experience may both be correct descriptions of the same reality, seen from different levels of organization, the way a description of a symphony in terms of air pressure waves and a description of it in terms of melody and emotion are both accurate and both incomplete on their own. One of the things that makes the physics of time so worth thinking about, apart from the intrinsic importance of the questions, is what it reveals about the relationship between the world as it is described and the world as it is lived. Science has an extraordinary capacity to reach beneath the surface of experience and find structures that experience alone would never reveal. No one would discover the block universe by introspection. No one would arrive at the relativity of simultaneity by sitting quietly and attending to the felt quality of time's passage. These are things that only become visible through mathematics, experiment, and the willingness to follow an argument wherever it leads, even when the destination is strange. But the world as it is lived does not disappear when science reveals the world as it is described. The two are not in competition. They are different kinds of access to the same reality, and each illuminates something the other cannot reach. Physics tells us that the flow of time may not be written into the fabric of space-time. Neuroscience tells us how the brain constructs that flow from memory, anticipation, and the threading of moments into narrative. Philosophy asks what any of it means for the experience of being a conscious creature moving through a life. None of these conversations is finished. All of them are worth continuing. What we can say, with some confidence, is that time is not what it first appears to be. The steady, universal, forward-moving river of common experience is a construction, not a false one, not a mistake, but a construction nonetheless, assembled by minds operating within particular thermodynamic conditions in a universe whose deeper structure does not obviously contain anything that flows. The experience of time is one of the most intimate and irreducible features of conscious life. The physics of time is one of the most unsettled and generative frontiers of contemporary science. The distance between those two facts is not an embarrassment. It is an invitation. We live inside time the way we live inside a language, so completely immersed in it that stepping outside even for a moment requires extraordinary effort, and what you see when you manage it is not a view from nowhere, but simply a different and wider view from somewhere else. The physicists and philosophers who have spent their lives trying to understand what time actually is have not escaped time. They have simply found ways of looking at it from angles that are not available in ordinary life. And what they have seen from those angles is genuinely surprising. Time may not flow. The present may not be universal. The past may not be gone. The future may already exist, in some sense, in the permanent geometry of a universe that does not move, but simply is. These are ideas that take time to settle into, which is fitting, perhaps, for ideas that are about time itself. There is no urgency in letting them settle. They will still be there in the morning, patient and open, waiting for the next moment of quiet in which to be considered again. If this was a good companion tonight, a like or a subscribe helps other curious minds find their way here.